In this video, we're going to see how to solve linear systems. Linear systems. And we're going to be looking for two functions, x and y, and the derivative of x with respect to t will be ax plus by, and the y with respect to t will be cx plus dy. Just to do a very easy example, let's suppose that we have dx dt equal 2x and dy dt equal y. Notice that here a is 2, b is 0, c is 0, and d is 1. Then here the solution is very easy because the solution of this differential equation is y equal c2 e to the t, and here the solution is x equal c1 e to the 2t. This is what is going to happen in general. We are going to be looking for the general solution, and the general solution is going to have two constants, c1 and c2, and sometimes we are going to, instead of asking for the general solution, we're going to say we want the solution that satisfies, it doesn't have to be 0, but let's say x of 0 equal 2, y of 0 equal 1. Then usually the procedure, not always, is to find the general solution, and then you want this function to satisfy this condition. Then when t equals 0, you get c1 e to the 2 times 0. You want that to be 2, and therefore you say c1 must be 2. And doing the same thing here, we get that c2 e to the 0, you want it to be 1, and that means that c2 must be 1. And therefore, the solution of the initial value problem, when you have this is called an initial value problem, is x equal 2 e to the 2t and y equal e to the t. So let's do something interesting here. What is the relation between x and y? Let's see if we can find a relation between x and y. For example, this solution, when t equals 0, you are here at 1, 2, and here at 1. X is equal 2 and y is equal 1, right? This is when thinking about x of t and y of t. Notice that x is always positive and y is always positive. That means that in this case, when you plot all the values x of t and y of t, you are always in this quadrant. And what happens if we do y squared? Notice that y squared is e to the 2t, right? Then essentially y squared is e to the 2t, and then we get that x is equal 2 times y squared. And therefore, in this case, if you think about this, x equals 2y squared, this is a parabola, half of a parabola that opens to the right. We will see later that this looks like that, right? That's the collection of points always in the first quadrant. Notice that if this 2 changes to the 3, then the relation would be like x equal 2y cubed, something like this. It doesn't have to be a parabola, but it's something that looks like that. Okay. But let's see what is going to happen in general. Then we're going to be explaining how to find the general solution when we have a, b, c, d, or the particular solution. The procedure to find the general solution is like this. We compute the matrix of the system, which is the matrix A, B, C, D, and then we compute the characteristic equation. Remember that the trace of A is just A plus D, and the determinant of A is AD minus BC, and And then the characteristic equation is lambda squared minus the trace of a lambda plus determinant of a equals 0. And then we solve this. We're going to see that there will be three cases. The case in which lambda 1 is different from lambda 2 and they are real numbers. We're going to call this the case of two real eigenvalues. And then the other case is when lambda 1 and 2 is of the form alpha plus or minus beta I, where beta with beta bigger than 0, complex numbers, and then there would be like another section that explains what to do if we have this situation. And the other case is when lambda 1 equals lambda 2. Okay, we're going to see these three cases. And in this video, I will be explaining how to do this case. Then this is the procedure. If you have, let me call this two different eigenvalues, two different real eigenvalues. Then what you need to do is you need to find two eigenvectors. Then you say for lambda 1, you find the eigenvector that goes with lambda 1. Remember that you do by solving this system. You do a minus lambda 1 times x plus by equals 0, cx plus d minus lambda 1 times y equals 0. This is a good thing to do the two equations, because you will see that these two equations are equivalent, or one of those equations is 0 equals 0. And then we want to find a particular non-zero solution, like a v1 and a v2. And we do the same for lambda 2. We set up the system, and then we find another eigenvector, which is w1 and w2. And then the general solution looks like this. It looks like xy equal to c1 e to the lambda 1t b1 b2 plus c2 e to the lambda 2t w1 w2. We can rewrite this in this form. We can rewrite it as x equal to c1 e to the lambda 1t. Let me erase these cases. We are not considering these cases anymore. Plus c2 e to the lambda 2t. Oh, sorry, I forgot here to write c1 x is c1 times v1, and here is c2 times w1 e to the lambda 2t, the first entries, and the y would be c1 b2 e to the lambda 1t plus c2 w2 e to the lambda 2t. Notice that the w1, lambda 1 and lambda 2 comes from the characteristic equation, and the v1, v2 comes from the eigenvectors. And the w1 and w2 come from this eigenvector. Let's do a particular example. Okay, let's have a particular example. I can keep this. Let's see. Let's assume that we have 4x plus y. 4x plus y. And the y dt is negative 5x minus 2y. Okay, then in this case the matrix is the matrix 4, 1, negative 5, negative 2, right? And the trace in this case is 2, and the determinant would be negative 8 minus negative 5, which is negative 3, and the characteristic equation is lambda squared minus 2 plus the determinant, which is minus 3, equals 0. And then in this case we can solve that by factoring lambda minus something, lambda plus something, and 3 and 1 equals 0. That means that lambda equal 3 or lambda equal -1. We are in the situation where we have two different eigenvalues. Then essentially, this is the lambda. We can take this to be lambda 1 equal 3, lambda 2 to be -2, but in order to find the v1 and v2, we need to find the eigenvector of this, and in order to find the w1 and w2, we need to find the eigenvector for that. Let's find the eigenvector for lambda equal 3. For lambda equal 3, the eigenvector is the matrix A minus 3 times x plus y equals 0, and here is -5 plus -2 minus 3 times y equals 0. This is the system x plus y equals 0, and -5 minus, -5x minus 5y equals 0. Then a non-zero solution of this would be x equal 1 and y equal -1. Then we put 1 and -1. Notice that here we have our v1 and v2. We do the same for lambda equal -1. In this case, to compute the eigenvector, we do A, which is 4 minus -1 times x plus y equals 0, and here is -5x plus parentheses -2 minus -1 times y equals 0, and this is the system 5x plus y equals 0, -5x minus y equals 0, and a non-zero solution of this is x equal 1 and y equal -5. Then the general solution is like this. This is the general solution. Xy equal to c1 e to the 3t times this vector plus c2 e to the -t times this vector. And if I just decide to see what is x would be c1 e to the 3t plus c2 e to the -t, and y is -c1 e to the 3t minus 5c2 e to the -t. What happened if we set up some initial conditions? Let's say if I don't want the general solution, if I don't want to find this general solution, but I want to find the solution that satisfies x of 0 equal 4 and y of 0 equal -1. What do? This is the general, we find the general solution, and then we find the constant c1 and c2 that satisfies this condition. Let's see how difficult this is going to be. It's going to be just solving a linear system. If we say c1, when we replace t by 0, we get c1 plus c2 equal 4. Right? And here, when we want y of 0 to be -1, that means that when t equals 0, we get -c1 minus 5 c2 equal to -1. Right? This is what we want. And how do we solve this system? We can add the two equations. If we add the two equations, we get -4c2 equal 3, and that means that c2 is -3/4. And from here, we have that c1 is 4 minus c2, that would be plus 3/4. c1 would be 16 19/4. That means that the solution of the initial value problem, of this initial value problem, is x equal x equals C1 19 over 4 e to the 3t plus C2. C2 is minus 3/4 e to the negative t, and the value for y would be minus 19 over 4 e to the 3t minus 5 times C2. 5 times C2, or 5 times 3 is 15. It would be plus 15/4 e to the negative t. This would be the solution of the initial value problem, and if I ask for the general solution, this will be the general solution. Okay, I think this is it for this part. In the next video, I will explain the following case. Okay, let's stop here.